Welcome everyone. Today I'm very excited to introduce you to the accompanying lecture series from my textbook Olympia Number Theory Through Challenging Problems. In this video series, we're going to go through my textbook together and also see some fun, challenging examples, including USAMO, Putnam, and other hard problems as we go along. So today we're going to be taking a look at the well-ordering principle and the principle of induction, which serve as the first two sections of the book. So to begin with, we need to explore and define what the integers are and what properties they have. So the set of integers are defined in the way that you see here on your screen. They are all the whole numbers that do not have any decimal points. My personal favorite integer is the number 42, but we're going to see lots of fun properties of many integers throughout this video series. We also have properties of addition and multiplication for integers a and b, which include the closure property, so the sum of two numbers and multiplication of two numbers are always both integers. The associative property, which is seen by the two equations you have on your screen. The commutative property, which means that if you add two numbers, the order is irrelevant, and multiply them, the order is also irrelevant. The identity, which is a number 0, that if you add any number to, you get the same thing back. And the number 1, which if you multiply any number to, you get the same thing back. The distributive property, and the addition of an additive inverse as well. Notice that there is no multiplicative inverse though, because that will get into the rational numbers, which we'll see soon. Positive integers are the numbers that are just greater than 0, and the additive inverse of the positive integers are the negative integers. The natural numbers, which is denoted by the letter n here, consist of 0 combined with the positive integers. And the integers are equipped with an ordering relation. We say that a is less than b, denoted a less than b, if b minus a is positive. So in that case, then the minimum of a and b is a, and the maximum of a and b is b. And there's an awesome theorem about the integers which really helps us out a lot, which is that every non-empty subset of the positive integers has a least element. And we say by definition that x is in S, which denotes that x belongs to the set S. So as an example of this, we can actually prove that there is no integer between 0 and 1. And think about it for 1 minute, but we're going to use a proof by contradiction technique. So to do this, we're going to assume for the sake of contradiction that the set S, which consists of all the integers between 0 and 1, is non-empty. However, then by the well-ordering principle, it must have a least element, say the number m. However, from the closure over multiplication property, we know that m squared is also an integer. However, because m is less than 1, we know that the square of m is less than m as well. Therefore, we found a smaller integer that is less between 0 and 1. So therefore, this contradicts the minimality of m, so the set S must be the empty set and there are no integers between 0 and 1. And this might seem like a very trivial result, however, a lot of results require us, in order to prove them rigorously, we have to go to all of our axioms and see where they're coming from. One of the famous examples of this is the proof that 2 plus 2 equals 4 is a several hundred page textbook, which seems like a trivial result that every grade school student should know. So we're now going to look at the principle of induction, which says, suppose we have a statement P that we wish to show is true for all positive integers at least 1. We can then prove this in 2 steps. We can show the base case, which means showing that P is true for 1, or it can also be showing that it's true for some small number greater than 1 as well. But if we want to show the property is true for all integers at least 1, we have to show that we can start from 1. And then the inductive step, which means we always show that we have a domino effect, where if we can show that p of k implies p of k plus 1 for any integer k is greater than or equal to 1, then basically we knock down the first domino of p of 1, and then we knock down all subsequent dominoes as well. And this assumption that we make is known as the induction hypothesis. Now this might sound a little abstract, so let's take a look at this through an actual example. So actually before we do that, I want to prove this fact for you, and I'm going to prove it by contradiction. So assume that the set S, which is equal to n, such that p of n is false, is non-empty. Then let the least element of S be m. So we're going to be using the well-ordering principle that we saw from the last slide. Observe that 1 is not in S, therefore m is greater than 1. So the reason for that is because we've shown the base case, so we know that p of 1 is true. Also, by the minimality of m, we see that m minus 1 is not in S. However, by the inductive step, then we know that p of m minus 1 is true, and then that also implies p of m is true, so we've arrived at a contradiction. So again, we kind of have a rigorous proof of the principle of induction along with a well-ordering principle proof of the principle of induction. So now let's look at that promised example. And for this example, I want to prove the identity that the sum of the first n cubes is equal to n times n plus 1 divided by 2 squared. And this might be a surprising identity for some of you that have not seen this one before, but it's actually a very useful identity that shows up all the time on mathematical contests and beyond. So to begin, we're going to prove the base case, which means we have to prove it's true for n is equal to 1. When n is equal to 1, on the left-hand side of the identity, we get 1 cubed, which equals 1, and on the right-hand side, we get 1 times 2 divided by 2, which is equal to 1 squared. So we get 1 equals 1 squared, which is a true statement. And we're now going to do the inductive step. So we're going to assume that the formula is true for n is equal to k. And notice that we substitute a kind of like dummy variable here for n, and that's just to make sure that we're not using any circular reasoning in our argument. So we use n is equal to k here, and we show that we assume by hypothesis that the sum of the first k cubes is k times k plus 1 divided by 2 squared. And we now want to show this is true for k plus 1. And in order to do that, all we have to do is add the next cube to the formula. So we're going to use the inductive hypothesis and add the k plus 1 cubed to this, and we're going to get on the left-hand side just the result of that plus k plus 1 cubed. And then on the right-hand side, we're going to get the formula squared plus k plus 1 cubed. And now we can factor that a little bit more. So we factor out the k plus 1 squared term, and then we're going to have k squared divided by 4, and then we're going to have plus an additional k plus 1 there. And now you might see where this is going, because if we write the right-hand side under a common denominator, we get that that's going to be k squared plus 4k plus 4, which is the same thing as k plus 2 squared. So we get the whole thing is k plus 1 times k plus 2 divided by 2 squared. And we've now shown that we've gone from n equals k to n is equal to k plus 1, so we've shown that this result is true in general. And notice that induction is not the only way to prove a result. We can also sometimes see a proof without words. And a proof without words here is going to be shown by an awesome example that comes from Alan L. Fry, which basically splices upon cubes to show that the sum of cubes is the same as the sum of 1 plus 2 squared. So 1 cubed plus 2 cubed is the same as 1 plus 2 squared, which is true because 9 is equal to 3 squared. And we can see that this relates back to the previous identity that we saw, because the sum of the first n natural numbers is the same exact thing as n times n plus 1 divided by 2. And now to wrap up this video, I want to look at a USAMO problem that uses induction. And it says, prove that for every positive integer n, there exists an n-digit number divisible by 5 to the n, all of whose digits are odd. And this seems like a very challenging problem. And where I would start with a challenging problem like this is I want to see this is true for small values of n. So to do that, I'm going to try it for n equals 1 to begin with. And I'm actually going to do this for several of the first base cases. So I do this for n equals 1, and I find the number 5, because 5 has all odd digits. For n equals 2, I need a multiple of 25. 25 doesn't work, 50 doesn't work, but 75 works, and I keep going in this one. For 125, I need a multiple of 125, and 375 fits the bill. And we can observe a pattern that seems to say that each time we're just adding a new digit on at the end of the number, or at the beginning of the number rather. So we're going to assume by our inductive hypothesis that we always are going to have a k-digit number that is divisible by 5 to the k. Okay? So all of these ace of i's are odd numbers. So n is a multiple of 5 to the k. And we write that as n is equal to 5 to the k times some capital A there. And now we're going to consider the k plus 1 digit number for I is in the set 1, 3, 5, 7, and 9, which just constitutes all of the odd numbers. And we're going to see that this number here, that this new number is going to have I in the front, and then it's going to have the k digits that we had previously, which was like going from 375 to 9,375. In this case, I would be equal to 9. And we can rewrite this number as I times 10 to the k, because that's the first part, and then the next part is just that number capital N, which we said before was 5 to the k times capital A. Notice that we can then factor out a factor of 5 to the k from the expression, and we get 5 to the k times I times 2 to the k plus A. Now, you might see where we're going from this, because we have to find a value of I such that the number there must be a multiple of 5. But we see that the set I there forms a reduced residue system, because they're the numbers 1, 3, 0, 2, 4 when you reduce them modulo 5. So therefore, there must exist an I such that I times 2 to the k plus A is equivalent to 0 mod 5, because 2 is relatively prime to 5. We'll see this fact more in a future video, but you can just take my word for it for now. But we can always find this value of I. And it might be fun to try playing around with a few examples of this as well. Now, once we have this multiple of 5, we can see that therefore there always exists a number n sub I that is a k plus 1 digit number whose digits are all odd that is divisible by 5 to the k plus 1. So we've proven our fact. Stick around for the next video where we're going to explore strong induction with a USAMO problem and a fun Putnam problem. We'll see you then.